In 1884, Svante Arrhenius came up with the ever-so-humble Arrhenius definition of acids and bases, where acids release hydrogen ions into water and bases release hydroxide. However, it was in 1923 when Bronsted and Lowry independently realized that it was simply a proton that is lost and gained in acid-base reactions. Together, they created the Bronsted-Lowry theory, which conforms much better to equilibrium equations. When speaking in terms of strengths of acids and bases, they were either strong or weak. Strong acids and bases dissociate 100% in water, while weak acids and bases dissociate less than 100%. When weak acids and bases react, they form equilibriums where the forward and reverse reaction balance out. There are a few substances that are capable of acting as acids or bases. These are called amphiprotic. They typically have an easily removable hydrogen and have a negative charge. Water is the exception in this, as its extremely polar charge makes up for not having an overall negative charge. Amphiprotic substances can act as an acid or base. These form conjugate pairs that only differ by one proton. Another thing to note is that acids are often defined by how many protons they can donate by using prefixes like monoprotic or diprotic. All weak acids and bases dissociate in water to some extent. The amount that they dissociate is called the acid ionization constant, also known as Ka. Kb works exactly the same, but for bases. Ka and Kb is the equilibrium of acids and bases and informs us how much of the substances dissociates, and therefore how acidic or basic the solution is. Basically, the more an acid dissociates, the more power it has. Strong acids and bases behave a little differently in that they dissociate 100% in water, and therefore do not form equilibriums. This means that strong acids and bases are all the exact same strength, as it is impossible to dissociate more than 100%, and when they are mixed together, they cancel each other out completely. The acidity of a substance can be measured by its pH, while you can measure how basic a substance is by its pOH. pH and pOH are inversely related and always add to 14, because as the acidity of a substance increases, the basicity of the substance decreases, and vice versa. You can find the molarity of a substance using the pH by using the negative inverse log button on a calculator. Water is normally a neutral substance that sits at 7 on the pH scale. This means the amount of hydronium ions equals the amount of hydroxide. However, temperature can affect this equilibrium, as adding temperature pushes the reaction towards the products.